Hello everyone, my name is Xiaogang Xu. I'm from the Chinese University of Hong Kong. Here I will present our paper, Hierarchical Image Generation via Transformer-Based Sequential Patch Selection. In this paper, we explore how to map a user-given scene graph to an image. It's challenging to generate an image from a scene graph consists of several objects with complex interactions, since we need to ensure that the synthesized images are consistent with the scene graph and the synthesized images are realistic enough with high resolution. Such a framework has its practical meaning. With such a framework, users just need to provide flexible scene descriptions to define the object as well as their interactions, and the framework would synthesize images, achieving a user-controllable generation process. Current frameworks for generating images from scene descriptions take advantage of generative adversary networks. Those theoretical models would solely learn on the networks to model the appearance of objects. Compared with the practical models, semi-practical approaches have recently been proposed and shown super performance. Such models first learn a memory bank to retrieve image corpus for objects in scene graph, and then synthesize realistic images from scene graphs and retrieve the crops. In such framework, the spatial arrangement of the objects in the images are defined by the scene graph, while their appearance are determined by the retrieved corpus from the pore. So there is a key requirement. The retrieved patches for generation should be mutually compatible for synthesizing an image and consistent with the corresponding scene graph. In this work, we focus on the semi-parametric model, improving the retrieval stage as well as the generation stage. For the improvement of the retrieval stage, we formulate the retrieval stage and complete it as a novel sequential process, where the selection of the crop for each object in the scene graph would be determined by the spatial style and content features of corpus that have already been chosen. And to refine the generation stage, we further propose a novel generator that generates realistic images from a scene graph, with selected image corpus as a guidance. Our overall framework can be divided into 3 stages. There are scene graph encoding stage, retrieval stage, and generation stage. In the scene graph encoding stage, we use the scene graph to extract semantic features which are useful for crop retrieval and location prediction for each object. In the second stage, the sequential crop selection module, that is called SCSM, sequentially selects a most compatible crop for each object given all previously chosen croppers, which will be used for image synthesis. To complete our sequential selection strategy, we propose to adapt a transformer structure that is trained with conjective learning. Finally, in the generation stage, the progressive scene graph to image module, which is called PSGIM, synthesizes the target image based on the scene graph features and select the croppers. Especially to synthesize the realistic and high-resolution images, we designed the generator with a hierarchical generation stage using the hierarchical gated convolutions and proposing patch-guided spatially adaptive normalization module. We have some notations. Give a scene graph G, which contains a set of objects O, which include O1 to On, and their pairwise relation R, including R1 to Rm. Our goal is to synthesize an image X from the scene graph. The height of an image is h, and the width of the image is w. Moreover, the height of an image patch is hp. The width of an image patch is wp. To complete the scene graph encoding stage, our method first processes the input scene graph to extract text embedding for all the n objects. The encoding is completed by the graph convolution network e.g. The feature of n objects are denoted as T1 to Tn, and the feature channel number of the embedding is Ct. For each object, we match the feature of T J with the text embedding of the object corpus in the external object pooling to retrieve a set of its candidate corpus. The retrieval, the candidate group for OI is denoted as MOI, and the TI can be used to predict the bounding box BI for the object OI. And for the second stage, we first need to select only one group for every object's k candidate corpus. Our method performs the corpus selection operation in an iterative way. Suppose there are already M corpus. The sequential corpus selection module, which is SCSM, aims to select one corpus from the candidate corpus, such as denoted as M, O, M plus 1. This is the overview of the SCSM. We propose a novel concept learning framework. In other words, given a chosen corpus set P from the same image, the compactable score between P and a new crop from the same image should be higher than the compactable score between P and a new crop from a different image. We use a novel transformer to implement this idea. Specifically, for every crop Pi with its protected bounding box location Bi, we embed both its appearance and position information as an input token to the transformer as Fi equal to W1 times Pi plus EB Bi. W1 is a trainable linear transformation matrix to convert Pi into 1D embedding with shape, and EB is a position encoder. Especially, we add a learnable part token F0 to represent the overall compatible features of all the input tokens. Its appearance input P0 is randomly initialized with the normal distribution. Its position input is initialized with Bm plus 1, which is the predicted bounding box location of the new object OM plus 1. Pm plus 1L denotes the negative patches that are not consistent with the chosen patches, and Pm plus 1 denotes the positive patches that are consistent with the chosen patches. Give a new candidate group. We first apply another trainable linear matrix with the same shape of W1 to obey its appearance features. Note that the embeddings are normalized. Then the compatible score with the chosen group set P is computed as a constant similarity between their embeddings. The conjective loss for this training image can be denoted as L conjective. During the inference, the selection is completed in an iterative manner. For the generation stage, we propose the progressive scene graph to image module, and this is an overview. To synthesize the realistic and high-resolution images, we use hierarchical gated convolutions and propose patch-guided spatially adaptive normalization module. We have some notations in this module. Our generation module first uses a content encoder EC and a style encoder ES to extract different features from the object or Pi. The output content feature CI is used as a generated input to provide the structure information of object OI in the generated image. The output style feature SI is used to modulate the content feature to have a unified style with the other object group. Our generator has a hierarchical structure with n output scales. Our style unifier takes as input the evaluated style features of all object corpus and proposes the output as the modulation parameters, which are applied to normalize the channel of each content feature CI independently. Well, this style unifier is implemented via MLP with several nonlinear layers. MUI and sigma I are the mean and variance of the content feature CI, and epsilon is a small positive constant. There are two important network components at every scale of the generator. The first component is the gated convolution, which aims to implant the missing area uncovered by any object corpus. The second component is a patch-guided spatially adaptive normalization module, PSANM. In PSANM, Our reference image RG is employed to predict spatially adaptive normalization parameters. In PSANM, we first group and pass the object groupers into a reference image and then use it to guide the structure and content of the generated image. Especially, the reference image RJ is generated by passing the grayscale of all object group PI onto an empty canvas based on their location. Given the generated image output at the J scale, we propose several laws to train our generator. First, for a training image Y with its paired scene graph, we use the graph ground truth groupers and bounding box for each object, and then use the generated output should be reconstructed the input. Besides the reconstruction loss in pixel level, we also use a perceptual loss. In addition, we apply the adversary loss with an discriminator at each scale. We also use a consistent loss term to encourage the similarity between the generated output and different scales. In summary, the total loss to train our generator at the O scale can be written as this, where lambda 1 to lambda 4 are loss weights. We use CocoStuff and VG for experiments, since CocoStuff and VG datasets are standard benchmark datasets for evaluation scene graph to image generation modules. We use 3 metrics including IS, FID, and DS. And there are 4 kinds of baselines. We conduct evaluation using 2 different settings. First, bounding box of objects are predicted by the models. Second, ground truth bounding box are given as inputs in addition to the scene graph. The results of those 2 settings are shown in this table, and our method has both better performance. We also show the results on the CocoStuff and VG datasets and the 2 settings of using predicted and ground truth bounding box, and those show the effectiveness of our framework. Our framework can synthesize diverse images by setting different groupers to initialize the set of chosen groupers in SCSM, and the diverse results can be viewed in this page. We also conduct a user study. In this user study, participants will see one scene graph and 2 images synthesized by our framework, and the one of the baseline. They will have to choose which one is better. Especially, they could also select that they have no preference. The results are shown in this table, and we can see that our framework can better complete the synthesis from scene graph to images. We also do some ablation studies. The first ablation study is used to prove the effectiveness of our proposed SCSM and PSGIM. And the results are shown in this table. Obviously, our retrieval process is better than baseline retrieval. Moreover, the ablation study also proves the advantage of our generator compared with the generator proposed by baselines. We also validate the effect of using the position embedding in our SCSM by removing the position encoding of bounding box in SCSM. And this setting is called SCSM without P. The results shown in this table also show that removing the position encoding causes the decrease of the performance. Moreover, we also analyze the impact of number of candidate groupers for each object. As shown in this table, the performance is improved a little since our retrieval module will preference sequentially choosing the candidate group that has a higher rank after per retrieval. Finally, we also set another ablation study to evaluate the grouper selection directly. First, we passed the retrieval groupers from different methods into one image, building a canvas. Then we sort the groupers according to their areas and put the groupers with a larger size to the bank. And next, we can compute the FID, IS, and DS for the canvas formed by different retrieval methods. The results show that our retrieval groupers are more mutually compatible than other baselines, and the position embedding is useful to improve the results, while previous methods fail to use such information. Okay, this is the summary. In this paper, we propose a novel sequential crop selection module and a progressive liaison graph to image module. Thanks for your watching.